Can I share? Can I share?
Just a minute. Let me introduce with my big honor next speaker today, Professor Olga Kharlampovich with City University of New York, who will tell us about formulas in random groups.
Okay, hi. I would like to share my screen. Mhm. Let's do screen mode. Okay, so thank you very much to the organizers for doing this, like 15th. I mean, not the same organizers probably have been doing this for 15 years, but like, I mean, that's a great idea, and it's very nice to see so many people at the conference. Okay, so I'm going to talk about formulas and random groups. And this is a joint work with Riza Sklinas and Alexei Mesnikov. And so let me tell you now how somehow it does not, it's not moving. Just 1 minute. Just somehow pages not turning. Okay. So it's like this. I just go back to the beginning. I think something happening in the full screen mode, so I'll do it in this mode. Okay, random groups in kind of my model were introduced by Gromov when he introduced hyperbolic groups. And he claimed that almost every group is hyperbolic. Can you hear me?
Yes, yes.
Yes, okay.
Yes.
So I'm going to work with Gromov's so-called density model and explain why it is like why a random group in this model hyperbolic. So we fix number n greater or equal than 2. And so take a free group on n generators, free group of rank n, and consider the set of reduced words in the generators of this free group of length L. Now take the number d between 0 and 1, which is called density. And so then a random set of relators at density d at length L is a subset of the set of words, which consists 2n minus 1 to the dl many elements, picked randomly among elements of the sphere of radius L. Now, so let's look at this number. So 2n minus 1 to the L, this is how many words of length L in n generators we have. So 2n minus 1 to the dl, so it is a subset, right? Because d is between 0 and 1. So now we consider a group given by these relators. So given by 2n minus 1 to the dl relators. And so a group, when R is a random set of relators of density D at length L, is called a random group of density D at length L. And R is a random set of relators of density D at length L. So basically, a random group, it is not a group. It is a family of groups. Like for each L, we have a finite number of groups at length L. And then we consider L going to the infinity. So we say that a random group of density D almost surely satisfies some property of presentations, let's say P, if the probability of occurrence of P tends to 1 as L goes to infinity. So again, so it's not a group, it is a model. For every L, like suppose we have some property P. For every L, so there is a subset of all our groups at length L, which satisfy P. And so this, as L goes to infinity, this fraction of representation satisfying property P should be larger and larger and larger. And basically, it should be almost all the groups of length L. Then we say that a random group satisfies property P. So again, does not want to, okay, maybe this. So Gromov himself claimed, and later Olivier like did the kind of all the details of the proof, that if G is a random group of density D, then for D less than 1/2, it is infinite torsion-free hyperbolic. And for D greater than 1/2, it is either trivial or Z2. So, or the group of two elements. So like when D is greater than 1/2, we have some sort of an identity crisis, because I mean, this is a property of presentation. So when D is greater than 1/2, that the group is either trivial or has two elements. Now for D less than 1/2, the group is infinite torsion-free hyperbolic. And at the H here, it is not clear what's happening at D equals 1/2. So we are going to be interested in groups at density less than 1/2. So after Alexei and myself, and also Tzlil Sala proved that three groups of different ranks have the same first-order theory, there were kind of different questions. Okay, so what happens to other groups? And Julia Knight formulated this conjecture that if you have a first-order sentence in the language of groups, then the sentence is true in a non-abelian free group, if and only if it is almost surely true in the random group. So actually, Julia just means a random one-related group. Because in this model, if we look at, let me return to the model. So when D is equal 0, we actually deal with one relator group. So density 0, we have a one relator group, or sometimes it's customary to think about a group with a fixed number of relations. Okay, and so here are the main results I'm going to talk about. With Rizas cleaners, we proved that, before one deals with first-order sentences, one has to understand what are the equations, how equations are behaving in the group. Because like a first-order sentence, so we have a quantifier prefix, and then we have conjunction of disjunctions of equations and non-equations. So suppose that V of X bar, let V of X bar be a system of equations. So then all solutions of the system in a random group, so in this model, in the Gromov density model at D less than 1/16, or in the Fourier-Lattice models, almost surely obtained by substitutions from solutions in a free group. So this is our result with Rizas. So what this means, that if you have a system of equations, then the probability that there exists a solution to the system in groups with relations of length L in the model, it actually that there exists a solution of the system which is not just the image of the solution in a free group, goes to zero when L goes to infinity. Now, using the same scheme, Sadhya Masala proved recently that the same result is true for d less than 1/2. And then what we can say? We can say that, like again, this is a result with results and already published, that if d is less than 1/2 and we have E sentence or Boolean combination of IE sentences, then indeed the probability that this sentence is true in a free group and wrong in a random group goes to zero as L goes to infinity. So that indeed IE sentences are the same, like in this random, which are true, are the same in the free group and in this model of random group of density less than 1/2. And at the end, I will say about the same result with Rizas, Klinas, and Alexei Mesnikov for arbitrary sentences. Okay, now what is used? What kind of techniques are used here? We use the same technique as Gromov and Olivier used to prove that groups are random group is hyperbolic for d less than 1/2. Just try to do the whole screen because now I have an idea how I can change pages. No, again, something strange happening. Okay. So one uses so-called Van Kampen diagrams. So Van Kampen diagram, like briefly speaking, it is a planar diagram used to represent the fact that a particular word in the generators of a group given by a group presentation represents the identity element of that group. So if an element, if a word like this is a labeled, it should be a label diagram. So we can think about this as a planar graph. So, and edges, there are edges of the diagram are labeled by the alphabet of generators of the group. So a word is equal, Van Kampen lemma states that a word is equal to 1 if and only if there is a Van Kampen diagram that we can read our word on the boundary of this diagram. Now, faces of the diagram should be labeled by the relations of the group. So Van Kampen diagram for a group, it is a diagram such that faces of this of the diagram are labeled by relations of the group. And so Gromov basically stated that linear isoperimetric inequality is satisfied in a random group. So if gamma L, let gamma L be a random group of density less than 1/2 at length L, then every reduced diagram D over gamma L almost surely satisfies the following linear isoperimetric inequality. So the length of the boundary of the diagram is greater than L times 1 minus 2D. So density is 1/2, so this is a positive number, times the number of cells in the diagram. So delta D is a boundary length, and this is a number of faces. And you know, if there is a linear isoperimetric inequality, then the group is hyperbolic. So one, like, there are two things, two ideas involved. So first of all, let me return to the diagram. So suppose we have suppose we have a kind of abstract one-camping diagram. Suppose we don't have labels. So one has to estimate what is the probability that we can fulfill this diagram by relators of a random group. And it is like it's not when we start fulfilling, for example, so here we have to write a relator, but then this relator has a common path with another relator, right? So if we can choose, if we can pick the first relator at random, then the second one, we already have restrictions, right? And for the third one, we also have restrictions. So to fulfill a diagram, one has to compute what is the probability that we can actually choose relators in the of length L so that they satisfy this. But then there is another problem. So, okay, we can prove, like I'll show later, or you just trust me, that, because it's not too much time, that actually the probability that either the boundary of this diagram is long, or the probability that this diagram is fulfillable goes to zero exponentially when L goes to infinity. But this is just one diagram, like one reduced one-camping diagram. The problem is that there are many diagrams, right? Like even for given L, we can have infinitely many diagrams, different diagrams. And here, like the hyperbolicity is actually a local property. Like in hyperbolic space, you can prove if you can prove hyperbolicity around in some neighborhood of some points, then there is this local to global property. So then you can prove that the space is hyperbolic. So for diagrams, this means the following, that if we take alpha, which we want to use, like just positive number L, for which we want to use in linear isoperimetric inequality, that for each such alpha, there exists a number k depending on alpha, and another alpha prime, such that for a group given by relations of length L, if we have a linear isoperimetric inequality for alpha, for reduced one-camping diagrams with at most k faces, then we have it for another alpha prime for any reduced one-camping diagram. So basically, one can bound the number of diagrams we have to consider. And if one can prove linear isoperimetric inequality for them, then it's true for any diagram. So this is what is local to global in kind of in Gromov-Olivier proof. Moreover, so if alpha is greater than 0 and density is less than alpha divided by 2, then with overwhelming probability, a random set of relators actually satisfies a small cancellation condition, C prime of alpha. Okay, now let me again say, let me repeat this, the first theorem about equations. So for density less than 1/2, and given a system of equations, that the probability that there exists a non-free solution for the system, solution which cannot be lifted to a free group, approaches 0 as L approaches infinity. So let's formulate this precise. Like a solution to system of equations V of x can be considered as a homomorphism H from the group given by generators, variables we take as generators, and system of equations we take as relations. So it is a homomorphism from this group into a group at length L in the model, into a random group. Right? So so solution, we say that solution is free or solution can be lifted if we can factor this homomorphism. So H is a solution. So solution can be, we can think about a solution as a homomorphism from this group given by relations which correspond to equations. In algebraic geometry, this would be basically a coordinate group of the system of equations. If the solution can be lifted to solution in a free group, so to a homomorphism to a free group, and then standard epimorphism from a free group on n generators into our random group. And so probability of existence of non-free solutions, this is what we proved, is zero as L approaches infinity. Now, and so how do we do local to global? To do kind of, we want to do the same. We want to bound the number of cells in the diagram, which we have to consider, so that if you can, yeah, and why we have to consider diagrams. That's another good question. Let me just jump here for a minute. So suppose we have an equation x, y, z equals 1. Then we can write like this. Suppose we have a solution of this equation. Then we can write the solution as a, like x we can write on one side of the triangle, y on the other side of the triangle, and z here. So then there exists a diagram, which is actually, we can think about this diagram as a geodesic triangle in the group with sides labeled x, y, z. Now, if you have an equation longer, for example, x, y, z, t equals to 1, then we can always say that x, y equals, let's say, x1, it's going to be triangular equation, and then x1, y, z, x1, z, t equals to 1. So every system of equations can be reduced to a triangular system, to a system of equations of length 3. Now, so basically, what means that something is a solution to system of equations which is not coming from a free group? It means that there is a system of triangles, of geodesic triangles in the group, in the random group, such that variables, such a solution is written on the boundary of these triangles. So the problem is even kind of, it's even harder to fulfill such a thing because like if in the proof of hyperbolicity, we only had to worry about like boundary between two cells, that it should be the same word on the boundary of two cells. Here, in addition, we have to make sure that, for example, we have x here and x in some other on the boundary of some other triangle, then it should be the same word. So it also puts more restrictions. So we can, like, for example, let me show you. So this is just an example. Suppose we have such a diagram and we have a system of equations like x1, x1, x4 equal to 1, x2, x2, x5, x3, x3, x6, and x4, x5, x6. This, like, to satisfy, to be able to write some words on the boundary of these diagrams, suppose in addition that we know the length of the solution. So suppose that our solution has length, here it is length 6. Then, like, this graph shows that, for example, this letter x11, like everywhere where it appears, it must be the same letter. So this shows that we have to put a lot of restrictions on the words to satisfy this diagram. And like eventually one can prove that the probability of this is not, that the probability of this goes to zero, as L goes to infinity. Now, how about local to global? Let me return to this. So if you have a finitely generated group G and there is a morphism to finitely generated group H, then the length of the morphism, this is just the sum of the images. The length of the morphism H is the sum of the length of the images. So using actions on R trees and so-called shortening argument, this is the most complicated part of the proof. We can show that actually, like that, so for D less than 116, and if we have, and so L goes to infinity, gamma L is a sequence of random groups, and HL are homomorphism from this coordinate group of system of equations here. And so if this, I mean, solutions can be short and they can be longer in this definition. So that, and so if you have a sequence of short non-free morphisms, then the length of the morphism is linearly bounded by, so it's a linear function of L and the constant. K is a constant. Now for D less than 1/2, the length of the morphism is bounded by L times the log square of L. So this allows to say that the bound of the number of faces in the diagrams which we have to consider for each L, we can bound by constant times log square of L for D less than 1/2 and by constant for D less than 1/16. Now the number of such diagrams is actually is a polynomial function of L. So the number of diagrams to consider for each L is a polynomial function of L. And the probability to fulfill one diagram, this is what I was explaining here, the probability that the diagram can be labeled by relations of group gamma L of length L in the model goes to zero exponentially fast in L. So what we have a polynomial number of diagrams. For each of them, probability to fulfill this diagram goes to zero exponentially in L. Then the probability to have a non-free short solution goes to zero as L goes to infinity. And now what is like how one like have to understand this result about formulas, that so if you have a sentence, right, so then for each L, so the proportion of groups which like if this sentence belongs to the theory of a free group, then for each L the proportion of groups satisfying this sentence is like very large. And as L goes to infinity, like this proportion, the ratio of the proportion of groups which satisfy this sentence to the set of all groups, to the number of all groups goes to 1 as L goes to infinity. Now let me skip universal sentences. So and basically, together with Alexei and Rizas, we prove that for D less than 1/2 and any first order sentence, the probability that this sentence is true in a free group while it's wrong in a random model goes to zero as L goes to infinity. So thus, in particular, proving Julia-Knight conjecture. Yeah, I think that's all what I wanted to say. Thank you very much.